Chapter 11: The Human Eye and the Colorful World. The Human Eye. Do you know which part of our body lets us to read the book? Check out a rainbow in the sky. See a vehicle heading towards our way. Or focus on things that are nearby or far away? Well, it is our eyes. Our eyes are one of the most important optical instruments gifted to us by God. The human eye is the gateway to one of our five senses. Our eyes are at work from the moment we wake up early in the morning up to the moment we sleep at night. It is an organ that reacts to light.
It is like a camera. It is the eye which makes it possible for us to have the knowledge of beautiful and colorful world around us. It is one of the most valuable and delicate sense organs. Let us study the structure and working of our eye. The eye is very nearly spherical in shape and is about 2.3 centimeters in diameter. There is a thin membrane on the eye called cornea. The cornea is a transparent spherical structure at the exposed surface of the eyeball. It is the portion which is bulging outwards. Light enters the eye through the cornea. The region behind the cornea is filled with a watery fluid called the aqueous humor. Cornea and the aqueous humor together refract most of the light entering the eye. Behind the cornea there is a dark muscular diaphragm called iris. It is the colored part of the eye. You might have seen different people having different colored eyes. It is due to the color of the iris which is different for different people. There is a small opening of variable diameter at the center of the iris called the pupil. It is the pupil controlled by the iris that regulates the quantity of light entering the eye. When the light is very bright, the muscles of the iris stretch over the pupil to reduce its size. When the light is dim, the muscles of the iris relax to increase the size of the pupil. The iris controls the size of the pupil and hence regulates the quantity of light entering the eye. This tendency of pupil to adjust the opening for light is known as adaptation. There is a crystalline, transparent and biconvex lens, that is, a lens having convex surface on both sides behind the pupil. The eye lens is composed of a fibrous, jelly-like material. The lens forms a real and inverted image of an object. The lens provides fine adjustment to focus the image on the inner surface of the eye. This is called the retina. The retina is a delicate membrane. It consists of large number of light-sensitive nerve cells connected to optic nerves. These cells produce electric signals when illuminated. There are two kinds of nerve cells on the retina called cones and rods. Cones are the cells that sense color and are sensitive to bright light. Rods are the cells which are sensitive to dim light. The signals produced by these cells are taken to the brain through optic nerves. The brain interprets these signals and processes the information contained in it, and an image of the object is perceived. A point where the optic nerve enters the eye is called the blind spot. Image formed at this point cannot be seen. Majority of the portion of the eye, that is, the region behind the lens and in front of the retina, is filled with liquid-like material called the vitreous humor.
The power of accommodation.
Let us see how our eye adjusts itself to see objects at different distances. The focal length of the eye lens can be changed by contracting or relaxing the ciliary muscles. The eye lens in relaxed position of eye muscles has a focal length of about 2.3 centimeters. In this situation, the lens is thin. Thus, the focal point of the eye lens is located on the retina. Hence, a normal eye in its relaxed position can form sharp images of objects located at longer distances. When we look at objects closer to the eye, the ciliary muscles contract. This increases the curvature of the lens and the lens becomes thicker. Consequently, the focal length of the eye lens decreases. When we look at a distant object, the ciliary muscles are relaxed, so that the lens becomes thin and its focal length increases. This enables us to see distant objects clearly. The ability of the eye lens to adjust its focal length is known as power of accommodation, and the process of focusing the eye on different objects placed at different distances is called accommodation. There is, however, a limit to the smallest value that can be attained by the focal length, because the ciliary muscles cannot increase the curvature of the lens indefinitely. Thus, the focal length of the eye lens cannot be reduced below a certain value. For a normal eye, the minimum distance from the eye at which an object can be clearly and distinctly seen without any strain on the eye is about 25 centimeters. This distance is known as the distance of distinct vision. If an object is placed closer to the eye than its distance of distinct vision, it cannot be seen clearly.
The least distance of distinct vision is also known as the near point of the eye, whereas the farthest point from the eye at which an object can be seen clearly is known as the far point of the eye. The far point of human eye is very large and is considered to be at infinity. We have seen that a normal eye can see nearby and distant objects due to its power of accommodation. But note that the rays of light coming from a nearby object diverge when they reach the eye. Hence, a convex eye lens of high converging power is needed to converge the light rays on the retina. On the other hand, the rays of light coming from a distant object or at infinity are parallel to one another when they reach the eye. Hence, a convex eye lens of low converging power is needed to converge them on the retina. We all have two eyes. You might have tried to see with only one eye open anytime. Have you ever wondered that if we can see with one eye open, then why do we have two eyes for vision and not just one? Well, there are many advantages of having two eyes. Firstly, it provides a wider field of view, and secondly, it gives accurate judgment of distance. A single human eye has a horizontal field of view of approximately 150 degrees and of about 180 degrees with two eyes. Thus, having two eyes gives us wider field of view. Also, having two eyes enhances the ability to detect faint objects. You might have seen that there are some animals, usually the prey animals, that have eyes on the opposite sides of their head. Can you tell the reason for this? Well, having eyes on the sides of the head increases their field of view so that they can see their enemies and protect themselves. But humans and some animals have their eyes situated in the front of their head. This reduces the field of view, in the favor of which it is known as stereopsis. Since the two eyes are located at different positions, each captures a view from its own perspective. The two separate images are sent on to the brain for processing. When the two images arrive simultaneously, brain unites them into one picture by matching up the similarities and adding in the small differences. The combined picture appears three-dimensional because it has the added depth dimension. This tells how far or close the object is. Defects of vision and their correction.
People wear spectacles because they have some defect in their vision. Some of your classmates may be wearing spectacles. They may be seeing the nearby objects distinctly but cannot see the blackboard writing clearly. There are some other people who can see the distant objects clearly but cannot see the nearby objects clearly. Also, there can be people who cannot see distant objects as well as nearby objects clearly.
These are the situations in which our eye loses the power of focusing images on the retina.
We know that our eye lens has the ability to change its focal length so that we can see distant and nearer objects clearly. This ability allows humans to see clearly objects at any distance between about 25 centimeters from the eye to infinity because the focal length is adjusted to form clear and sharp images on the retina. This is called accommodation. The defect in vision can occur due to various reasons like weakening of the ciliary muscles, change in size of the eyeball, irregularities on the surface of the cornea, formation of membrane over the eye lens, etc. Because of the defects in the eyes, one loses the power of accommodation of the eye and cannot see objects distinctly and comfortably. The vision becomes blurred due to refractive defects of the eye. Such defects of vision can be corrected by use of spectacles. There are three common refractive defects of vision. Let us discuss these defects and their remedies. Myopia. This defect arises due to slight elongation of the eyeball or due to bulging of the eye lens so that the distance between the eye lens and the retina is greater than the normal eye. A person suffering from this defect can see nearby objects clearly, but is unable to see objects at long distances. The image of a distant object is formed in front of the retina instead of on the retina. This defect is known as myopia or nearsightedness. It can be corrected by using spectacles having concave lenses of suitable focal length. The concave lens diverge the rays of light passing through it. Hence, the parallel rays of light coming from a distant object are diverged to some extent before they are incident on the eye lens. Therefore, the image of a distant object is formed on the retina, and hence the distant objects can be seen clearly.
Let us calculate the power of concave lens to correct myopia. The focal length of the concave lens needed to correct myopia in a person is calculated by using the formula 1 upon f is equal to 1 upon v minus 1 upon u, where u is the distance of the object to be taken as infinity and v is the distance of the person's far point. Knowing the focal point of the lens, we can calculate the power of the lens using the formula. Power is equal to the reciprocal of its focal length in meters. The SI unit of power is diopter and is denoted by D. Let us solve an example to calculate the power of a concave lens to correct myopia. Solved example. A student suffering from myopia has a far point of 1.2 meters. What is the nature and the power of lens required to rectify this defect? Solution. The eye defect myopia is corrected by using a concave lens spectacles. Let us first calculate the focal length of the lens. The far point of the myopic student is 1.2 meters, that is 120 centimeters. This means that the distance object, that is, object kept at infinity, is clearly visible to the student if the image of the object is formed at his far point. So, in this case, the distance of the object u is equal to infinity. The distance of the image formed in front of the eyes v is equal to minus 120 centimeters. The focal length is given by the formula 1 upon f is equal to 1 upon v minus 1 upon u. On substituting the values, we get 1 upon f is equal to 1 upon minus 120 minus 1 upon infinity. The minus sign is because the image is formed in front of the lens. Since 1 upon infinity is equal to 0, we get 1 upon f is equal to 1 upon minus 120, or 1 upon f is equal to minus 1 upon 120. Thus, focal length of the lens is equal to minus 120 centimeters, that is, minus 1.2 meters. The power of lens is equal to the reciprocal of its focal length, that is equal to 1 upon minus 1.2, which is equal to minus 0.83 diopters. Thus, the power of lens required to correct the eye defect myopia is minus 0.83 diopters.
Hypermetropia. A person suffering from this defect can see distant objects clearly, but is unable to see nearby objects even after straining the eye. The image of a distant object is formed on the retina, but the image of the nearby objects is formed behind the retina instead of on the retina. The defective eye cannot produce enough convergence in an incident parallel beam of light. This defect is known as hypermetropia or long-sightedness. This defect is caused due to two possible reasons. 1. Weak action of ciliary muscles cause low converging power of eye lens. 2. Slight fattening of the eyeball in the horizontal direction, due to which the distance between the eye lens and the retina is decreased. It can be corrected by using spectacles having convex lenses of suitable focal length. The convex lens converge the rays of light passing through it. Hence, the rays coming from the nearby objects are converged to some extent before they are incident on the eye lens. Therefore, the image is formed on the retina of the eye, and hence the nearby object can be seen clearly.
The focal length of convex lens used to correct the eye defect hypermetropia is calculated using the formula 1 upon f is equal to 1 upon v minus 1 upon u, where u is considered to be as the normal near point of the eyes, which is 25 centimeters, and the image distance v is the distance of the near point of the hypermetropic eye. Knowing the focal length of the convex lens, its power is calculated. Let us solve an example to calculate the power of a convex lens to correct hypermetropia. Solved example. The near point of a person suffering from hypermetropia is at 50 centimeters. What will be the nature of and power of the lens required to correct the eye defect? Solution. Let us first calculate the focal length of the lens. The near point of the hypermetropic person is 50 centimeters. This means that the person can see the object kept at 25 centimeters clearly only if the image of the same object is formed at its own near point, which is 50 centimeters. The eye defect hypermetropia is corrected using convex lens spectacles. So, in this case, the distance of the object U is equal to minus 25 centimeters. The negative sign is because the image is formed in front of the eye lens. The distance of the image, that is, the near point of the defective eye V, is minus 50 centimeters. The focal length is given by the formula 1 upon F is equal to 1 upon V minus 1 upon U. On substituting the values, we get 1 upon F is equal to 1 upon minus 50 minus 1 upon minus of 25, which is equal to minus 1 upon 50 plus 1 upon 25, or 1 upon F is equal to 1 upon 50. Thus, focal length of the lens is equal to 50 centimeters, that is 0.5 meter. The power of lens is equal to the reciprocal of its focal length in meters, that is equal to 1 upon 0.5, which is equal to plus 2 diopters. Thus, the power of convex lens required is plus 2 diopters. Let us study another defect of vision which occurs in old age. It is known as presbyopia.
Presbyopia. This is an age-related defect. For a normal eye, we know that the least distance of distinct vision is 25 centimeter. This position of the near point depends on the accommodation capacity of the eye. However, as a person grows old, the crystalline lens grows in size and the ciliary muscles become weak, so that the power of accommodation is reduced. As a result, it becomes difficult to see nearby objects clearly. Position of near point recedes away from the eye with the age of human beings. This recession of the near point is called presbyopia and generally occurs at the age of 40 years. This is also called as old age hypermetropia. At an age of 60 years, the near point of the range of visibility shifts to about 200 centimeters. As a result, it is difficult to read and to see the hole of a needle to put a thread through it. You must have seen older people having difficulty in performing these actions. A person suffering from this defect has to wear spectacles with convex lenses like in hypermetropia. If a person is suffering with two defects like myopia and hypermetropia or presbyopia, two lenses are to be used. These are put in the same spectacle. Such lenses are called bifocal glasses. In a bifocal lens, upper part is a concave lens to correct myopia and lower part is a convex lens to correct hypermetropia.
Cataract. Cataract is a very common defect and usually experienced in old age. Sometimes the crystalline eye lens becomes hazy or even opaque due to old age. Also, decoloration of protein and subsequent appearance of cloudy eye lens results in the development of cataract. Thus, cataract is the loss of transparency of the crystalline eye lens. It cannot be corrected using any kind of lenses. Ideally, the vision of a person can be restored back after getting operated for cataract surgery. An artificial lens is fitted in place of the defected lens.
Facts about eye. Do you know that our eyes live even after our death? Do you know that we can light the life of a blind person by donating our eyes after our death? We are one of the fastest growing economies in the world today. Ironically, we also shoulder one of the largest populations of the visually impaired. Corneal blindness is one of the most common causes of blindness in India. Is corneal blindness curable? Yes, it is. How? Well, by donating our eyes. Let us know some facts about eye donation. Eyes can be donated only after death. An eye donor can belong to any age group or sex. People suffering from diseases like diabetes, hypertension or asthma, and those suffering without communicable diseases can donate their eyes. Even people who use spectacles or those who are operated for cataract can still donate their eyes. Eyes must be removed within 4 to 6 hours after death. The entire procedure of eye removal takes only about 10 to 15 minutes. Eye retrieval does not cause any disfigurement of the face. Persons who were infected with or died because of AIDS, hepatitis B or C, rabies, acute leukemia, tetanus, cholera, meningitis, or encephalitis cannot donate their eyes. Only corneal blindness can be cured by eye transplant. If the donated eyes are not found suitable for transplantation, then they are used for research or teaching purposes in medical colleges. So, let us pass this gift of vision to the blind people. Refraction of light through a prism. Have you ever seen a prism? A prism is a wedge-shaped block of glass bounded by 3 similar rectangular surfaces, ABEF, ACDF, and BCDE, and 2 triangular ends. The opposite faces of the triangular ends, that is, ACDF and BCDE, are not parallel to one another. They are inclined to one another, and the angle between them is called the angle of prism. That is, angle ACB is the angle of the prism. While drawing a ray diagram, the triangular prism is shown by drawing a triangle. Let us now study the refraction of light through a glass prism. Let us understand the refraction of light through a triangular prism by performing an activity. Fix a white paper on a wooden drawing board. Place the prism on the paper in such a way that its triangular base rests on the paper. Mark its outline and name it as ABC. Remove the prism. Draw a normal NN dash to the face AB at point Q. Draw a straight line PQ inclined to AB. Now, place the prism on its marked position ABC. Fix 2 pins P1 and P2 on the line PQ about 5 cm apart. Observe the images of these pins through the face AC of the prism. Fix 2 more pins P3 and P4 such that these pins appear to be in a straight line with the images of pins P1 and P2. remove the prism. Remove the pins and mark their positions. Draw a straight line RS passing through the point P3 and P4 such that it meets the other face AC at the point R. Draw a normal MM' to the face AC at point R. Produce PQ and SR backwards to meet each other at point T. Join Q and R by a straight line. Here PQ is the incident ray, QR is the refracted ray, and RS is the emergent ray. Note that the ray of light enters from air to glass at the first surface AB. So, the light on refraction bends towards the normal. At the second surface AC, the light ray travels from glass to air. Hence, it bends away from the normal. The angle made by the incident ray PQ with the normal NN' is the angle of incidence, that is, angle PQN is equal to angle I. The angle made by the refracted ray QR with the normal NN' at the face AB is the angle of refraction, that is, angle N' QR is equal to angle R. The angle made by emergent ray RS with the normal MM' is the angle of emergence. Therefore, angle MRS is equal to angle E. Angle RTW is equal to D is the angle of deviation. This is the angle which the incident ray makes with the emergent ray. Repeat the experiment for different values of angle of incidence and measure the angle of emergence E and angle of deviation D in each case. You will notice that the emergent ray of light always bends towards the base of prism. Also, the emergent ray is not always parallel to the incident ray of light because the opposite faces of the glass prism where the refraction takes place are not parallel to one another. The value of the angle of deviation D depends on the angle of incidence I. Dispersion of white light by a glass prism.
Sir Isaac Newton was the first person to show experimentally that sunlight consists of 7 colors. He passed a narrow beam of sunlight through a glass prism and obtained a band of 7 colors on a wall. The phenomenon of splitting of white light into its 7 constituent colors is known as dispersion of light. Is there a way to get the 7 colors from white light? Let us try a different experiment to see this. Let's first get into a dark room where we get a beam of sunlight from the window. Close the window of the room in such a way that you get only a single beam of sunlight. Take a cardboard and make a fine hole through it. Now, place the prism on a table. Place the cardboard so that the sunbeam falls on the prism at a slant. Now, place a white screen on the other side of the prism. What do you observe? You will observe a band of 7 colors called the spectrum being formed on the white screen. The colors are distinctly visible on the screen. The color red is at the top of the spectrum and the violet at the bottom. Orange, yellow, green, blue and indigo appear in the middle in that order. From the activity, we can infer that the sunlight consists of 7 colors.
Do you know what is the cause of dispersion of white light into different colors? Let us explore this further. The refractive index of the material of the prism is different for different colors. White light is composed of 7 colors, therefore the constituent colors get refracted through different angles and hence are dispersed. The red light deviates the least while the violet band deviates the most. Let us understand what happens when dispersed light from one prism is incident on another inverted prism. Activity: take a source of white light, two identical prisms, a white cardboard, and a screen stand. Place one prism on the board with its base facing the observer. Allow white light to be incident on one of its surfaces. We observe that white light passes through the prism and gets dispersed in constituent colors, while emerging from the other face. Now take the other prism and place it on the board with its edge facing you and the base away from you. Let the dispersed light from the first prism be incident on that face of the second prism which is facing the first prism. Place the screen to obtain the image of the emergent beam of light from the second prism. You will be surprised to see that the emergent light is nothing but a beam of white light again. Can you guess why? Well, this happens because the dispersion produced by the first prism is equal and opposite to that of the second prism. Hence, the separation of constituent colors by first prism is annulled by the second prism, and once again the beam of white light is obtained. This observation was a landmark in the study of dispersion of light, as it gave Newton the idea that the sunlight is made up of 7 colors. Do you know that the formation of a rainbow is combined phenomena of refraction, dispersion, and reflection? Let us proceed to understand this. Formation of a rainbow. On a rainy day, when the sun is also visible in the sky, you might have seen a beautiful rainbow in the sky opposite to the sun. The rainbow comprises of bands of 7 colors. Do you know how this wonderful optical phenomena occurs? It is interesting to learn that the suspended water droplets in the clouds act as many small prisms and disperse the sunlight into different colors. The suspended water droplets acts as a small prism. The sunlight incident on the water droplets gets refracted and disperses into its 7 constituent colors. These rays get internally reflected and pass to observer after one more refraction at the drop surface. The constituent colors of light get dispersed in different directions and beautiful color bands are seen. The occurrence of a rainbow clearly indicates that the sunlight is made up of 7 colors. Where else have you seen the dispersion of light by water droplets? Well, if you glance through a waterfall with the sun behind you, a beautiful 7-colored arc can be seen. Similarly, in the evening, if you stand in front of a water fountain with your back facing the sun, you can observe a beautiful rainbow through the fountain.
Atmospheric refraction. The refraction of light caused by the Earth's atmosphere is called atmospheric refraction. The formation of mirage, twinkling of stars, or the advanced sunrise and
Delayed sunset
are some of the optical phenomena in nature. Let us learn about them in detail.
Mirage. Have you seen reflections of vehicles on hot sunny days giving rise to water-like appearance on the roads? Does the water really exist? No. Then how is such an optical illusion formed, and what is it called? Well, this type of optical illusion is called as mirage. Due to heating, air near the ground becomes warm and less dense. The upper layers of the air are comparatively cooler. The refractive index of air depends upon its density. Hence, the variation of temperature of air layers at the surface of the road and the air layers above it create a gradient in the refractive index of the air. A ray traveling from optically denser medium to rarer medium bends away from the normal. Therefore, ray traveling towards the ground bends away from the normal as it passes through lower hot layers. At a certain level, the ray gets internally reflected and travels towards the observer. Now, as the ray travels from a rarer medium to a denser medium, it bends away from the normal in the successive layers. The rays appear to be coming from the reflected image of the object. Consequently, the illusion of water is experienced. Do you remember any other example of this kind of optical illusion? At the time of Holi, you might have seen the flickering of objects through the turbulent hot air above the fire of Holi. As air above the fire is constantly moving due to convection currents, the object seen through it appears to wobble. These are some other effects of refraction, which we observe in our day-to-day life. Let us proceed to understand a global effect of refraction, the twinkling of stars. Twinkling of stars. Have you ever wondered why the illuminating bodies called stars twinkle when you look at the sky on a dark, starry night? We know that stars are self-illuminating heavenly bodies. They are point sources of light, as they are very far away from the earth. Generally, they are seen in the darkness of the night only. The layers of the atmosphere act as a rarer medium at higher altitudes. Hence, the refractive index increases gradually as the rays of light reach the Earth's surface. As a result, the rays emitted by the stars undergo deviation and the apparent position of the star is slightly higher than its actual position. Since the atmosphere is not stationary and undergoes a constant change, the apparent position of the star is also not fixed and keeps on changing. When more light is refracted, we see a bright star, and when less light is refracted, the star appears dim. Hence, the stars appear brighter sometimes and fainter at other times, giving a twinkling effect. If you observe the sky, you can notice certain objects which, although do not twinkle, but appear luminous. What are these objects? They are planets. Can you explain why the planets don't twinkle? Well, planets are more close to the Earth as compared to stars. Hence, they appear quite large in size when viewed from the Earth. Therefore, a planet can be considered as a collection of a large number of point sources of light. The rays of light from these point sources also undergo a similar kind of refraction while passing through Earth's atmosphere. If the intensity of light from one point source decreases due to fluctuations in the atmospheric conditions, it is found to increase simultaneously from some other source. Hence, the average intensity of light of the planet remains constant. Therefore, planets don't twinkle. Do you know the effect of atmospheric refraction on the sunrise and sunset? Let us understand this. Advanced sunrise and delayed sunset. An interesting effect of atmospheric refraction is the phenomena of advanced sunrise and delayed sunset. The atmosphere is rarer as we go up. The sun rays reaching Earth get deviated and the apparent position of the sun appears slightly higher than its actual position. When the position of the sun is below the horizon, the rays coming from the sun get deviated as they pass through the Earth's atmosphere. The rays follow a curved path and reach the Earth. That is why the sun is observed 2 minutes before it comes above the horizon. Hence, the sunrise is advanced by 2 minutes. Similarly, during sunset, the sun moves below the horizon. However, it is still seen by an observer on the Earth. Hence, the sunset is delayed by 2 minutes. Thus, the atmospheric refraction increases duration of the day by 4 minutes. There are many phenomena that we experience where atmospheric refraction is evident.
Scattering of light. You might have observed that the sky and the water in the deep sea appear blue in color. Do you know the mystery behind this? Well, the blue color of the sky, the blue color of water in the deep sea are all spectacular phenomena observed due to the scattering of light. Scattering of light can be defined as reflection of light in random directions due to the particles present in the medium. The scattering of light takes place in the atmosphere due to the presence of dust particles, smoke particles, tiny water droplets, and molecules of air. The reddish appearance of sun during sunrise and sunset is the consequence of scattering of light by the particles present in the Earth's atmosphere. Before understanding more about this, let us know the Tyndall effect. Tyndall effect. A fine beam of sunlight traveling through vacuum or clean air is not visible. But if the same enters a smoke-filled or a dusty room, its path becomes visible. This is because the tiny particles present in the room scatter the beam of light. The scattered light enters our eyes and the beam is visible. This scattering of light by the particles in its path is called Tyndall effect or Tyndall scattering. It is named after the Irish scientist John Tyndall. The Tyndall effect can be clearly observed when sunlight passes through the canopy of a dense forest. The tiny water droplets in the mist scatter sunlight. It is also seen when headlight beams are visible on foggy nights. In liquids, the Tyndall effect can be easily seen by using a laser pointer. The laser beam can be easily seen as it travels through a colloidal solution. In a colloidal solution, particles remain suspended in the medium without dissolving completely. The color of the scattered light depends on the size of the scattering particle. Very fine particles scatter short wavelength light, that is mainly blue light, whereas particles of larger size scatter long wavelength light, that is red light. If the size of the scattering particles is sufficiently large, then the scattered light appears white.
How can you distinguish reflection from scattering? Consider a parallel beam of light incident on a polished surface like a mirror. As the rays in the beam are parallel to each other, they are incident making same angle with the normal drawn to the surface of the mirror. Therefore, according to the law of reflection, all rays get reflected, making some angle of reflection equal to the angle of incidence. Consider the beam of parallel light incident on a rough surface like a brick. Now, the surface of the brick being irregular, different rays are incident, making different angles of incidence with the normal to the surface of the brick at the point of incidence. Hence, the different rays are deflected in different directions, and we say the light is scattered by the brick. Do you know why the danger signal lights are red in color? Well, the effectiveness with which small particles scatter light is inversely proportional to the wavelength of light. Red light has the longest wavelength and hence is scattered least by the fog or smoke. Hence, the red light can be easily seen even at a distance. That is why the danger signal lights are usually red in color. Let us proceed to perform an interesting activity to understand another instance of scattering of light. Activity: take a set of watercolors. Select red, orange, yellow, green, blue and violet watercolors. Take a watch glass and put a drop of red color on it. To that, add 2 drops of orange color, 2.5 drops of yellow color, 3 drops of green color, 6 drops of blue color, and 10 drops of violet color, and mix them together. Which color do you get? You get a shade of blue color. Scattering of light takes place in the atmosphere with a similar proportionate scattering of components of light. As the atmospheric molecules are very small, light of smaller wavelengths is scattered more than the longer wavelengths. Therefore, scattering of light is not uniform. Light of blue color is scattered more than the other colors. This gives rise to blue color of the sky. Let us understand this in detail.
The blue color of the sky.
In the atmosphere, there are molecules of air along with some other smaller particles. When sunlight passes through the atmosphere, the sunlight is scattered by the air molecules present in the atmosphere. The size of air molecules and other atmospheric particles is very small compared to the wavelength of visible light. Therefore, light with smaller wavelength is scattered more than light of longer wavelength. The light of blue color and violet color is scattered more compared to the red and near red colors. Therefore, when you observe the sky, blue light is more prominent. Hence, we say the sky is blue. Thus, due to the scattering phenomena of light, the sky appears blue. Do you know the color of the sky appears dark to the astronauts? Well, there is no atmosphere at higher altitude. The astronauts do not receive any light and the sky appears dark to them.
Color of the sun at sunrise and sunset. Have you seen the sky and the sun at sunrise and sunset?
The sky and also the sun look reddish-orange at times of sunrise and sunset. This is also due to the scattering of light. Let us perform an activity to observe effects of scattering of light by colloidal solution in the laboratory. Activity: take a strong source of white light S, 2 convex lenses L1 and L2, a glass beaker, clean water, a cardboard with a hole at the center, and a screen. Place the source of light S at the focus of convex lens L1. The rays coming out of the convex lens L1 are parallel. Place the beaker filled with 250 ml of clean water in the path of light. Place the card having hole at the center on the other side of the beaker. Use the other convex lens and focus the light coming out of the circular hole on the screen. You will see a bright circular patch of light on the screen. Do you observe the path of light through the water when viewed from the sides? You do not observe the path of light through the water when viewed from the sides because the light passes through the water without any scattering. Hence, from side, you do not get to see any scattered light. Now add about 25 grams of sodium thiosulfate to the water and in the beaker and stir the solution till it dissolves. Then add 1 drop of concentrated sulfuric acid in it. A chemical reaction takes place and particles of sulfur begin to form in the water and a colloidal solution is obtained. Now what do you observe when you view the beaker from the sides? You see blue light coming from the sides of the beaker. This is due to the scattering of blue color by the sulfur particles present in the medium. Now, observe the image of the hole on the screen. What do you observe? The image of the hole on the screen looks reddish.
It is due to scattering of light that the sky appears blue and the sun red at the sunrise and sunset.
At the time of sunset and sunrise, the sunlight has to travel a longer path through the atmosphere before reaching observer. That is why the sunlight reaching the observer is more reddish-orange in color. Therefore, the sky and the sun disk look reddish-orange at the time of sunrise and sunset.
You might have observed that the sun appears white at noon. This is because at noon the sun is overhead and thus the sunlight has to travel a relatively shorter distance through the atmosphere. As the distance to be traveled is short, only a little of blue and violet colors of the white light are scattered. As a result, the light coming from the horizon has almost all its component colors in the right proportion, due to which the sun appears white to us.